Okay, as you can see, we begin something new today. Um, this is probably the second largest chapter that we cover throughout the school year, second only to that of stoichiometry, and that won't be until you come back from Christmas break in January. But with this chapter, part of it is a review from some concepts we've done earlier this year, but all of it is a review from what you had learned from physical science. And further we get into this, you're going to probably look at, yeah, I remember this. Yes, I remember this. So some of you maybe want to grab a book. I mentioned it while I was in there. You might not have heard me, but page 221. Yep. 221. Yes. So actually, page 220. We'll go ahead and look at that. Okay. Okay, so once you get to page 220, what I want you to do is probably what's the major difference that you see? Well, there's a couple of major differences between the cations and the anions. On page 220, bottom of page 220 and the top of page 221. Lower left-hand corner of 220, top right-hand corner of 221. Okay, what's the major difference between cations and anions? Yes. Which one's positive then? The cations are. Now, that's the first major difference. The second one, what do you notice is the difference with the naming of those ions? Like, look at the top right-hand corner of page 221. You're looking at the element fluorine. When that becomes an ion, what you change it to fluoride. Okay? If you see, for instance, oxygen, chances are you're going to change that to what? Okay. So what happens with cations like potassium and magnesium? Do you change the names of those? No, they just stay the same. The reason we say that is when we're looking at these, we want you to be able to say, well, if we're having this, and we're going to combine that with, we'll say, chlorine. Chlorine, okay? You need to know what the symbol for each element is, and for calcium, that is what? What's this? Ca. So, do we change this to calciumide? No, because the cations you just leave the same as what the metal it is that you're talking about. But when we talk about chlorine and we want to put these two together, what's the symbol for chlorine? Okay, so that is Cl. But when we form an ion with that, it's not calcium chlorine anymore. It's what instead? It's calcium chloride. When these ions, when these elements form ions, well then you change the name. It goes from INE to IDE. Oxygen does that, fluorine, all of the halogens, whether it's iodine, bromine, chlorine. If it's an anion, you change the suffix. So, with this, you can use your periodic table, but you would not need to to see that for what charge calcium is because it's in the second column. So since it's in the second column, it has a charge of plus what? And that's right, Y. How many electrons is it giving away? It's given 2 electrons away, so therefore that forms a +2 charge. Okay? Then, chlorine being a halogen, or now the chloride ion, which is a halogen, forms what charge? -1. Okay? And we're not just making these numbers up. Where are you getting possibly these numbers from? Yeah, and it tells you on the periodic table what charges these form. Okay. So the last thing, what do you suppose you got to do with those 2 charges? Yes, they need to add up to what? Add up to 0. This is starting to kind of, yeah, I kind of remember this. So we want the least common multiple, not the greatest common factor. Okay. So the least common multiple is the largest number that both of them would divide into. And that is 2. Now, the reason we say that, just for argument's sake, if you just do this and say, well, it must be 1. Well, that's fine for this. But what happens when you make a fraction here? It makes it 1/2. There is no such thing as calcium 1/2. So, if that's not the case, we don't want the greatest common factor. We want the least common. I think my math is correct, but it is the least common multiple for sure. Okay, so then therefore we change that to 2. Now, this is has nothing to do with the value. Okay, there's no such thing as a -1 chlorine atom or chloride atom. It's just saying it's negatively charged because it gained an electron. Okay, and if we will make sense of that in just a moment. So what's 2 divided by 2? And then what's 2 divided by 1? Okay, and don't get hung up thinking I got to put -2 down there. No, it's not the value, it's just the charge. Okay, so some of the concepts that you had learned over the last 3 weeks or maybe even a month. So if we look at calcium, if we did the Bohr model for that quickly, you'd say, well, we know we've got 20 protons in the nucleus. And how many more? Okay. Then if we do 1 chlorine atom, and then how many go in there yet? Okay, now someone said 5, that's correct. So it's in the 7th column, that's where those 2 numbers come from, but only in the P block, we're saying that chlorine's in the 5th column, which it is. So how many more electrons does chlorine want to become stable? It only wants 1 more. You're holding 1 up, that's correct. Well, look how many potassium has to give away. It's got 2 of them. So what can happen, since calcium's such a nice guy, where you got your 1 chlorine atom over here, and then we see there's another one, 17, and 2, 6, 2, and 5. So remember, it wants to gain 1 more electron, which it does. So 1 gets shot over here, and the other one over there. So how many electrons are in here now? 18, right? So how many protons are still in the nucleus? 20. So that still leaves a charge of positive. That's where that number comes from. This chlorine atom had 17 protons, but then look what happened. It gained 1. So 17 plus -18 gives you -1. And that's where that number comes from. Okay? So you're taking some of the concepts that you had learned this last month, Now we're putting them to use as far as naming these compounds. Okay, so that was a quick review of what we've done this last, like I said, 3 weeks to a month. Okay, or just recently, remember we said metals go in the middle, so it has 2 electrons to give away. There's 1, there's 2. So then here's in column 7. So it wanted to gain 1, it got it, and then there we go. There's your calcium chloride. All of this is old news. You can put this stuff behind you. Is that where you say hallelujah? So that's what you were doing on the floor earlier. Okay. Someone just went, oh. Oh, okay. I thought maybe you were saying hallelujah. No more dot diagrams. No, I'd rather try to tip a cow. Yeah. Friends like that, who needs enemies, right? Okay. No, I'm just kidding. Okay. So, what do you suppose it means on page 221 to be a monoatomic ion? Look at all them that you see there. Gosh, no. No, it's these that you're going to have to memorize, and these down here. Okay? So, what we mean by that, okay, we're going to want you to, we'll associate what these polyatomic ions, those you're going to have to know. Okay? These, you're going to have to know as well, the acids. So, if we keep it really simple, or try to keep it simple, okay, a monoatomic ion just means, can someone give me an example of that? We just went over 2 of them. Chloride is a monoatomic ion. What else could you use? You use calcium, you use chloride, you could use tin. Okay, it's just one element that forms one charge. So any one of those, perhaps 100 elements that you see on your periodic table, is an example of a monoatomic ion. Now, when we talk about a polyatomic ion, that's a little different. We're not quite that far yet. Okay, so what's true about the D block elements? D block elements, the majority of them. Silver is an exception to that. Yeah, no, they're metals, but what's, for the most part, how many, do they all just have one charge? No, like I said, silver and zinc are kind of exceptions to the rule there, but just someone go ahead and pick a D block element. Manganese would be a good example. Now, one of the things we want to make sure that you put +3 for manganese on your table. If it's not on there, I highly suggest you do that. Because down the road, and I believe when we do our lab series on qualitative analysis, manganese, he's bothering me too. Talking about the fly? Yes. Manganese is one of the elements that you would want to try to identify. It's got a +3 charge to it because they're all nitrates. The reason we use nitrates is that they're water soluble. Okay, that doesn't mean anything to you right now, but further down the road, that'll mean a little more. Make sure for element 25 that you put +3 in there. Okay, so that table on page 221 is just giving you many of the common monoatomic ions on there. And notice we said a D block metal. That's on the bottom of that table, on table 1, where you see, for instance, manganese is on there. We just said it's +2. It can also be +3. Tin can be +2 or +4. So you see many different types of ions on there that can have more than one charge. So there's got to be a reason to have them Roman numerals there, because how do you know you're referring to bismuth plus 3 or bismuth plus 5? Well, you really don't know unless you see that Roman numeral on there. But that's one that's not very common as far as what you see on this table. So some of you gave examples like, for instance, you said this, that's a monoatomic ion. You said this, that's a monoatomic ion. You could say even this one, plus 3, iron, which can be plus 2 or plus 3. So it just means one element that forms one distinct charge within any given example. So that's a monoatomic ion. So when we look at polyatomic ions, on the other hand, what do you suppose that means? What's a polygon? Yeah, multiple sides. So what we want you to do is turn forward to page 226. Now, there isn't a whole lot on there that we need you to memorize, but we are going to write them down that you will be responsible for. And if you get this the first time through, once you learn it and understand it, it's not that big of a deal anymore, because it'll be yours to keep. Right in the center. Hopefully Minnesota can turn things around tonight. Hit the ball right in the middle, right in the, not at the end of the bat, but on the beefy part of the barrel, other than the end of the bat. In the what spot? In that spot. That's right. Okay? Some say the sweet spot, well, whichever. It's where the ball jumps off the best. Okay. So, of the polyatomic ions, we want you to know. There's only 5 of them, I think. Now just look at that table on page 226. Look at how many different polyatomic ions there are. There's probably, 20, I'm going to say 22 on there. I'm just guessing. Did you get them? No. Okay. So, okay, 26. Fair enough. So, what we want you to know on page 226 is, we'll start with this one. The only positive one that you have to know is this one. NH4 is what? Ammonium. Okay? Okay? So, the rest all have negative charges to them. So, one of them is hydroxide, which is OH. OH has a charge of negative what? No. Negative 1. Okay? Negative 1. Hydroxide. Okay? Well, what about if we put NO3? Now the rest of these, the last 4 we're going to do, yes, go by what element has in it. Since it has nitrogen in there, it is nitrate, which has a charge of negative what? Negative 1. Okay? We're going to just take these in a decreasing order. In other words, we did the only positive ion you need to know. Now, those are only 2 negative polyatomic ions you need to know that have a negative 1 charge. Now, we're going to go through 2 of them that have a negative 2 charge. And one of them is sulfate, so it must have what element in there? Sulfur. And that is SO4, sulfate. And what charge does it have? Negative 2. Another polyatomic ion, if it's carbonate, it must have a charge of negative what? Negative 2, and it must have what element in it? Okay. And then I believe there's just one more we want you to know. Yes. So there's only one of them that has a negative 3 charge that we want you to know. Take a guess. You got a 50-50 chance. Really? Well, look up here and see once what we got left that you might need to know. In that far right-hand column that has a negative 3 charge. Yes, phosphate. Okay? So the formula for that is what? It's got a negative 3 charge, we said. So if it's phosphate, it must have which element in there? And how many oxygens? Okay? So PO4 with a negative 3 charge. One of the things that I think frustrates students is not understanding the difference between a polyatomic ion and a monoatomic. Because one of the things that can happen is when you're writing these compounds out, say we got calcium nitrate, and they're looking all over their table for the nitrate ion. Why can you not find it there? Because that's polyatomic ions, and the periodic table is only what type? Monoatomic, so that's why you can't find them. Okay? Then finally, there are just 3 acids that you're required to know. But look at what elements that you have go by your negative charges. Okay? So HCl is perhaps which acid? Hydrochloric acid. What do you suppose H2SO4 is? You're close. Sulfuric acid. And then finally H3PO4 is what? Phosphoric. So we got hydrochloric acid. We've got sulfuric acid. And then finally phosphoric. Okay? So those acids you need to know. Okay? And I don't know if it happens, I suppose it can be in any sport, that, gosh, we're going to have an insurmountable task ahead of us. Minnesota tonight, they host New York. My gosh, it's going to be a tough game. Well, it should be because it's the playoffs. This Friday night, you host Del Rapids St. Mary's. Yes, it's going to be a tough game. It should be. You ladies host Chester. It's probably going to be a tough game, which it should be because the opponents, you ladies are pretty good. Well, they maybe are too. Well, let's do our best to emerge victorious, whether it's tonight or Friday night. Hopefully we can start and end the week on a high note. That would be our goal. Okay. So, is anybody confused on the difference between a monoatomic and a polyatomic ion? All right. So, we're just going to do a couple of examples, and then the rest of the time then will be yours. Okay. And just think of it this way. Before there were, oddly enough, people used to navigate to get from point A to point B, they used to use a map. Didn't have their phone all the time. Kind of like old times, right? But just for let's say we'll just keep it simple. And really, there's 3 routes to get to Brookings from here, isn't there? Would you agree? Okay? Probably the most common would be what? Taking the interstate. That'd be the most common. Okay? Then maybe the next most common would be old what? Old 77. Okay? But you can't take that route right now. Okay? And then the least common, which is maybe possible, is a long ways out of the way, but you could do this. Do what? Highway 81. Now, let's say, for instance, or if you had to go to DeSmet, if the weather was good, which it is now, and there was no road construction, how many of you, without a map or without a phone, well, you have your phone, but you can't use the maps on there. How many of you know how to get from here to DeSmet without a map or a phone? Okay? And yeah, you could probably figure it out. My point is since you're raising your hand, you probably will never have to look at a map ever again because you learned and understood, and it's not that you memorized it, you just use that information. So it's yours to keep. This information that you just wrote down. It's not that you are not going to memorize it. It's just when you use that, it's going to be knowledge for you to keep. And it may take a little bit of time, but when you need to recall that information, it's going to be right there. Because your brain works very much like a file cabinet, or just like finding a file on your computer. You have to open up Word or Excel or whatever. You got to click on File, and then you got to find the right disk. Okay? Then once you find the right drive, then you got to click on maybe the right class, and then you click on the little file folder. Then you click on the little icon that has the document that you're looking for. Okay? That's how your brain looks. When you're putting this away, it's going to categorize this, and that information will be there. You just need to get maybe the right trigger for that. Okay, so someone give me a positive monoatomic ion. Okay? Someone give me either a mono or polyatomic negative ion. Okay? So here's our compound, ammonium sulfate. Okay? So now that we see that, what is the formula for the ammonium ion? And don't be looking at your periodic table, because ammonium is what type of ion? It's a polyatomic, so it's not going to be found in your periodic table. NH4. And then what's the formula for the sulfate ion? Okay? Now, when you get to this point, I always say go by your negative ion. Always start with your negative ion, because that's always going to have one distinct charge, whether it's -1, -2, or -3. Because when you get to your positive charges, you could be dealing with a D block element, which can have, like manganese can be +2, +3, +5, +6, maybe even +7. What does it say in there? I can't see it from here. Element 25, how many different charges are in there? Okay? Okay? So that's why we say go by your negative ions. Okay? So with that, you correctly said, at least I think you mentioned, what's the charge for the sulfate ion? And what's the charge for the ammonium ion? So those don't add up to 0. Least common multiple. Okay? So there's nothing wrong with doing this, just putting that number on top every time. So what's 2 divided by 1? Okay? So the answer that you get is what you write below in subscripts. And that's what you had done with that calcium chloride, was it? Okay? So 2 divided by 1 gives you 2. What's 2 divided by 2? Do we need to write 1 down there? No, it's just understood that you have one. Just like your hydrochloric acid, you don't write H1Cl1 or H2S1O4. You can, but I think if you had a college professor that saw this, where did you learn chemistry from? I mean, it's not that you don't have to, you just would look kind of silly doing that. And how many of you, maybe at the JV level, I think it's still possible in volleyball, you may have someone serving. What's a little different that you might see? Probably really, really common in junior high, less common in JV, but never in well, I wouldn't say never, but yeah. You even see this at the varsity level? No. Okay. Do you see this at the JV level? Yeah. Well, when you say not really, it does happen. But okay. Okay. So, is there anything wrong with what's written up there as it stands right now? There is something wrong. You do need to fix it. You need parentheses. Now, it's one thing to say you need parentheses, it's another thing to know where they go. Right. Because if you don't change anything, chances are we know what you're referring to. But what are you saying right now? We don't have 42 hydrogens. We wanted 2 ammonium ions. So right now we've got 1, but we wanted 2, so you have to put parentheses around that. So now we've got 2 ammonium ions. This did not change. Okay? Now that's simple math. Yep. So, nitrogen has an atomic mass of what? And how many do we have? Okay? Okay? Hydrogen has an atomic mass of what? Okay? So, mistakes can be made if you're going in a hurry and you just do some, and it'll probably happen. That could probably happen if you're going too fast, or it happens. So then, since we needed that, we'll just do it twice now. Okay? Sulfur is 30 something. 32? Okay? And then finally, oxygen. 1 oxygen is what? And then we've got 4 of them. So you add all them together. Sometimes I'm off by 10. Can we confirm that it's 132? You're just saying that. Gesundheit. Yeah. But that's the last thing we want you to do is calculate the atomic masses of these. Left outside, you on the bus. Left middle. Middle. And right middle. I guess we didn't have a right outside. Okay. So one of the things if you're looking ahead, really this chapter does not end until we get all the way up to approximately, it's just AMU. It would be grams otherwise. So you got to get all the way up to page 249. So as you can see, with this, we're going to be naming compounds. You're going to determine molar masses of substances. In other words, what that means is we might say if we have 300 grams of ammonium nitrate, what's the molar mass of nitrogen in that compound? In other words, how much of nitrogen only is within that entire compound? Okay? Or you might find out the percent composition. Then the final part of this chapter is determining chemical formulas mathematically with different breakdowns. And how that gets analyzed is something called a gas chromatograph. Do you still use that up in Brookings? Maybe it's a mass spectrometer now, maybe. But what happens is it's just an instrument that you take. Who can we pick on in here? Okay. So would you hire any of these? Oh, I'm sorry. Besides Cole, who else can we pick on in here? Adam. Okay. So if that's the case, darn it. You finally get the chance to run the ditch witch. You don't have to dig all the holes all the time. Well, he thinks he's going to do that, so he jumps on the ditch witch, and you're thinking, I'll be darned, I'm not going to do that. I'm going to take this shovel, and I'm going to wallop him upside the head and knock him off. Believe it or not, there are little tiny particulates that would probably be somewhere around the cranial region because he just got knocked out. Well, we're glad you're still here. But what you would do is you would take a chemical swab of that and you put that in that mass spectrometer we're just talking about, and that would give you a chemical breakdown of the type of metal that's left in his skull. Okay? Then what you need to do as a forensic scientist, okay, we got the up of what's in there, but we have nothing to compare it to. So what do you have to do secondly as a forensic scientist then? Gotta find the shovel that he had and compare the particulates on that shovel to what's on, and maybe hit him again. I don't know, wake him up. Okay? So that's part of the science behind this that you'll be doing. Yes? Yes. Okay, we will catch up to you next time. And we'll all be here. Right? Yeah. Adam, we want you to come back. All right.